everyone, this is Elizabeth Reagan of the Society of Plastics Engineers, and I'd like to welcome you to today's eLive presentation, Polymer Thermal Analysis. Our program today will be about 1 hour in length, including a question and answer session following the presentation. I will instruct you at that time on how to address your questions to the speaker. Also, if you would like a handout from this presentation, you may print one by pressing the Handout button at the top of the screen. The icon appears as 3 white sheets of paper. If you have any technical difficulties during the program, please press *0 on your telephone to contact customer care. They will be happy to assist you. Today's presenter is Jennifer Brooks. Jennifer received her BS and PhD in chemical engineering from Virginia Tech. Her graduate work involved the thermal degradation of polycarbonate and structure property relationships. She worked at Mead West Vaco in the research department prior to joining Polymer Solutions Inc. in 2002. She has served as the thermal group leader and is currently the technical services and senior project manager at PSI. Jennifer has several refereed technical publications and 1 U.S. patent. Jennifer, I'll let you take it from here.
All right, thank you. Good morning, everyone. As Elizabeth mentioned, my name is Jennifer Brooks, and I want to talk to you a little bit today about some thermal analysis techniques and how you might be able to use these to solve problems that you may have in your workplace. So first I want to kind of tell you what we're going to talk about. I'm going to go over some polymer backgrounds so that we're all on the same page. We'll talk about several thermal techniques then, kind of the alphabet soup we have here. Differential scanning calorimetry, thermogravimetric analysis, thermomechanical analysis, melt flow index, and dynamic mechanical analysis. And we'll go over some real-world examples for all of those as well. And have a couple case studies to go through, and we'll summarize and address any questions you might have. So one of the most important variables related to thermal behavior of polymers is their morphology. For our purposes, we're going to simplify and say that we're going to be in one of 2 states. We're either going to have an amorphous system, like that shown on the left, where our chains have no order relative to each other. They're simply entangled and kind of a spaghetti-like situation that we see here. And the other option is a semicrystalline system like we see on the right. Now, in that case, we have some ordering of the chains. They have a specific orientation relative to each other, but between those areas of order, there are amorphous regions connecting those together. Because polymers, just like any other material, are subject to entropy, we can't have a completely ordered system, so it's always going to be partially crystalline. So, focusing a little bit on the amorphous areas, the most prevalent transition we talk about there is the glass transition, or TG. And that's something that occurs only in the amorphous areas. It happens when you put in enough energy such that you impart mobility to the chains. Now, this can be translational motion, basically flow of the polymers, or it can mean that you have segmental motion of maybe 40 to 50 carbon atoms along the backbone, and they're able to move around a little bit. The temperature that this occurs at is dependent on several variables, things like free volume, which is simply the area between chains, attractive intermolecular forces like hydrogen bonding, the stiffness of your backbone, chain length or molecular weight. And I do want to say here that when I'm talking about putting energy into our samples, for our purposes, basically that means heating them up. So I mentioned backbone stiffness is affecting TG, and we have an example of that here. On the top left, we have polydimethyl siloxane. And this polymer has an oxygen in its main chain. And that oxygen linkage has a lot of flexibility. There can be rotation around that, and as such, you don't have to put as much energy into the system to get a lot of mobility, and therefore it has a very low TG of minus 127 or so. At the opposite extreme, we have polyphenylene sulfone. Now it has a nice bulky phenyl ring in its backbone, and as such it's a stiff chain. You're going to have to put a lot more energy in, and its TG therefore is much, much higher at about 500 C. Pendant group can also affect things because it affects our free volume. What we see here are 4 different polymers where the backbone chain is the same in each case, but the pendant chain is increasing each time. Now, when we have a longer chain like that, it makes it more difficult for different chains to get close to each other, and therefore there's a lot more free volume between them, which means there's more area for mobility, and therefore the TG decreases as you increase that side chain. Now the other main transition, which is only present in thin crystalline systems, of course, is the melting point, and that goes hand in hand with crystallization. So crystallization we're defining as when you have an ordered structure with some specific distance between chains. When you put in sufficient energy to overcome those bonding forces, we have melting, and simply the chains become disordered and your sample will flow. Where that temperature occurs depends on factors just like TG. Symmetry is one, because in order to build up into an ordered structure, your chains need to have a lot of symmetry so they can fit together nicely. Intermolecular bonding or hydrogen bonding can also have an effect. Branching can be important because, again, if you have bulky side chains or branches, that may interfere with the ability of your chains to order, and your chain length or molecular weight can be important as well. So here we see a couple of examples of those effects. On the left, we have nylon 6,6, and in these chains, we have carbonyl oxygens that really like to line up with the amine hydrogens and form hydrogen bonding. So that's a driving force for these chains to line up next to each other and form crystals. So nylon 6,6 is usually found in a crystalline form. Tacticity is another effect, and that's related to stereochemistry or symmetry of your molecule. The symbiotic polystyrene here in the middle has phenyl rings that are alternating on different sides of the chain. And you can imagine that if another chain came and lined up with this, they would fit together very nicely. Atactic polystyrene, on the other hand, has those phenyl rings just randomly along its chain, and therefore it would be very difficult to pack these together closely. And indeed, atactic polystyrene is typically amorphous. So now we've kind of gone over TG and TM. What does this mean for our polymer systems? Well, this is a generic modulus temperature graph where we have modulus along the y-axis and temperature on the x. We see that as we begin heating our sample, we see a drop in the modulus, and that's going to correspond to our glass transition. Below that, we have a glassy polymer, and above that, we're in the rubbery region. You might want to know where this is. If you want a polymer that's glassy at room temperature, for example, you would know based on TG that you wouldn't want to choose the polydimethyl siloxane we talked about a moment ago, because it's certainly going to be in the rubbery region at room temp with its TG at -127. So that would be an application for this. If you continue heating, you may see a second drop for semicrystalline systems that corresponds to the melt of your sample. So this will be important in processing because you have to make sure that you're in the melt state, but you don't want to go up so hot that you're going to burn the sample or degrade it. So using different techniques of thermal analysis is a way to get some of this information that you can use in your processes. The first thing I want to talk about is differential scanning calorimetry, or DSC. It typically requires a very small sample, about 10 milligrams or so. You can see on the left where a sample is being prepared. Basically, we carefully weigh out a sample, place that in an aluminum pan and seal it, and then we put it in our instrument, which is shown on the right. And we have TA Instruments thermal equipment in our labs. So how does this machine work? Well, we have our sample on one side of a stage and a reference pan on the other side. And this is the same type pan as you use for your sample. It simply doesn't have anything in it. Each of these stages have heaters, and the instrument functions such that the heaters supply enough power to keep these two sides at the same temperature. And that difference in power is related to the heat capacity of the sample and can be used to give us information about the different transitions that are occurring. Now, most of the time, we're going to be ramping at some known rate, perhaps 10 C a minute, and we're usually using nitrogen as a purge gas so that we're not having any kind of reactions occurring in our instruments. So what can it tell us? DSC can provide a wealth of information. Most of the time it's used to determine things like TG and TM, but it can also give us degree of crystallinity. It can help us determine heat capacity, and in some cases thermal conductivity of samples. Of We can measure how much a cured sample has cured. We can determine physical aging, look at the rates at which crystallization occur. We can measure oxidative induction time, which is related to oxidative stability of the sample. A newer technique is modulated DSC, which allows us to separate out overlapping thermal events. But I do want to point out here that the results that we usually get from these techniques are heating rate dependent. So if you're comparing your data to someone else's, you want to make sure that they were done under the same conditions. But you can see that DSC gives us lots of information, so it is one of our real workhorses in our lab. So here we see a hypothetical DSC scan. Our y-axis is heat flow, and in this case, exotherm is pointing upwards. That's important to note because some people use the opposite sign convention, so you want to be sure you take note of that when you're looking at a DSC scan. Our x-axis is temperature, and we see that as we are increasing the temperature, we see a step towards the endotherm, and that's how TG looks on these scans. If we continue heating, we might see an exothermic peak, which is related to crystallization. And further heating, we usually have an endothermic peak, which is melting. Now, the areas of these two peaks gives us an idea of how much crystallinity is in the sample and how much was actually occurring during your scan. If you have a system that can cure, you may see an exothermic peak related to cure or cross-linking. And if you continue heating, you might oxidize or decompose your sample. Typically, that's not something desirable for this particular instrument because you'll wind up contaminating it and affecting subsequent data. But we'll see one instance in which we actually do that on purpose. I do want to mention that normally you would never see all these transitions for one sample, but we kind of combine them here just for simplicity. So now for some applications. One thing that we can tell from DSC is the effect of processing. The first heat scan gives us data about the polymer itself along with its thermal history. So we can use the DSC to differentiate between samples with different histories. We see here the top curve in green is a raw material. The blue curve is the sample that's been processed, and the red curve is after it's been sterilized. And you can see some pretty marked differences between these. You can see a melting point in the raw material that isn't really so prevalent in the other two samples, and that may mean that this sample is a fairly slow-curing material. So after we've heated it to the melt and erased its crystallinity, it doesn't have time to to crystallize again as you're processing. We also see an endothermic peak overlaid on our glass transition, and this is related to physical aging. We've mentioned free volume of our samples. Well, if you get up near the TG but not quite to TG, the chains have the opportunity to move around a little bit and get rid of some of that free volume or space between chains, and this is manifested in this kind of a peak. The size of that peak is indicative of how much the sample's aged, and if we went above the TG, that would be erased, and we'd see a step transition only. Now, if we do a second heat of this sample, we will have normalized the thermal history, erased everything previous, and that may be useful to determine if you have differences in lots of material, because that second heat is just indicative of the material itself. In one study that we did at Polymer Solutions, we had an acrylic device that we were taking through an accelerated aging protocol to see how it might react to certain conditions. And one of the ways that we tested it was with DSC. The green curve at the bottom is the sample as received. The blue curve is 2 weeks, and the red curve is 8 weeks. And we can see that we're getting some droppage in our TG. It's going from about 111 down to 106. So this indicates that the conditions under which we're testing are actually starting to degrade the sample a little bit. So this is an easy way to get a handle on that. And again, it's a real small sample size. You may be able to do some other tests with other parts of that material that you were aging and still have those available after